Okay. What would you like to do?
Just the stuff you've been working on with your other geometry students' works.
Okay, let me get my book. Because everybody for a while was working on proving congruent triangles. And since then, everybody's kind of gone different paths. Properties of triangles. Do you have a book? Remind me.
I do, yeah.
You do. It's the same one as mine, right?
Yep.
Have you started chapter 5 yet?
We've been just getting, today we did proofing, it was like something about a parallelogram.
Okay.
And then we had to prove like two of the angles are equal.
Right. In other words, if you have a parallelogram, that's defined by having opposite sides that are parallel. Okay,
yeah.
So that side's parallel to that side, which makes each of these other lines a transversal. Okay, so
yeah.
that means that angle and that angle have to be supplementary. One of them's acute, the other one's obtuse. And it means that because that's a transversal also, that one has to be supplementary to this one. And I don't mean to make those equal, but it turns out that that one is equal to that one, and this one is equal to this
one. Okay.
And that's really pretty much all you need to memorize about a parallelogram is that opposite angles are equal, adjacent angles are supplementary.
All right.
Just kind of going through chapter 5 here. Let's see. Oddly enough, I have not gotten, for a while, everybody was doing the same thing, and now they're not. I know what's coming up, though, I think. Concurrency. Points of concurrency. Does this sound familiar at all?
Yeah.
Good. Let's review it, because it's one of those things in geometry that you have to know for geometry, but you don't have to know after that. In other words, for the ACT test, you don't need to know it. You don't need to know it for the SAT test. There's no test you'll take unless you try to become a professor in geometry or something where you'll have to know these. But they are kind of interesting. And it's all about, oops, you still there? Mark, I didn't lose you, did I?
No, you didn't.
It's all about finding the middle of a triangle. Sounds like a simple task, but it depends on what you mean by the middle. There are actually various middles. And these various middles go to different points of concurrency. Let's talk about the first one. Concurrency of perpendicular bisectors of triangles. And a perpendicular bisector. If I take the bottom side here and I bisect it, and I draw a perpendicular line, okay, and then I do the same thing with this side. I bisect it, and I draw a perpendicular line. And then I do the same thing with this side, and I draw a perpendicular line. Turns out that all three of those intersect at the same point or at a concurrent point.
Okay.
Okay? And you're going to have 4 of these. I can't even spell perpendicular. This is the perpendicular bisector. And this is called the Circumcenter. You're going to also run into an Ortho Center, an end center, and a centroid. So there's 4 things you're going to have to remember.
Okay.
Circumcenter is called that because, let's talk about this particular, when I do perpendicular bisectors of each side, and they find a point in the middle, turns out that that point is the center of a circle that would circumscribe that triangle.
Okay.
You know the difference between circumscribe and inscribe? If
No.
I inscribe a circle in a triangle, that's what I'm doing. If I'm circumscribing it, I'm going around the outside vertices.
Okay.
Okay, so this one's in, and this one is circum. Well, it turns out that because of the way I constructed this triangle, this circumcenter is equidistant from each vertex. In other words, that's the same distance as that, which is the same distance as that. So that's the special property of perpendicular bisectors. If you take any triangle and you create a circumcenter, like I did, by bisecting each side and drawing a perpendicular and see where they intersect, then you will end up with a center that is the same distance from each vertex. And understand this, that's a little odd because I started from the sides, and I get a center that is the equidistant from all 3 vertexes. Okay, today I'm only probably going to cover 2 of these. The second one, actually one of the more important ones, is if you have a triangle and you bisect each angle. In other words, I'm going to start with the angles. Okay, I'm going to bisect that angle. I'm going to bisect this angle. You know what bisect means. And I'm going to bisect this angle. So that that angle is equal to that angle is equal to that angle, and this angle is equal to this angle. Okay? This center is called an end center. And the reason is that this center is equidistant from each side. In other words, if I measure that distance right there, let me use blue here, hold on. This is tough to keep straight too, but that's why it's good we're going to get a little head start on you. I lost my pen. Okay, there it is. Can't see it. The blue lines are the same distance.
Okay.
These 3 blue lines. In other words, if I start by bisecting each angle, where they intersect is a point that's equidistant from the sides of the triangle. And what that means is that I can draw a circle, since all radiuses are the same. I can draw a circle inside that triangle. I can inscribe it. So that's the way you want to remember this, is the circumcenter is equidistant from the vertexes, oops, hold it. I wanted to do this. Just a second. Let's see, we created this perpendicular bisectors, and it results in equidistant from the vertexes of the triangle. I created this one starting with the angles and bisecting the angles, and I ended up with a center that was equidistant from the sides, the exact opposite.
All right.
Okay. And again, those are all the same, just like these three blue lines are the same length. Just a second, I'm looking for interesting applications of this. There is one other kind of center let's talk about.
Okay.
There's actually two others, but the one that maybe makes the most sense to use. If, in other words, if I were to ask you which of these is the true center of a triangle, you wouldn't really be able to answer me. There's no true center of a triangle. There's the circumcenter, there's the end center. There is something, however, that one would say probably would represent a true center of a triangle. And that is, if I had a piece of cardboard that was shaped like this triangle and it was the same thickness,
okay,
and I were to try to balance that piece of cardboard on a pencil, get the picture?
Yeah.
In other words, I'm looking at the top of this, but if I was looking at it from the side, there's my piece of cardboard, and I got a pencil right there that I'm trying to balance that piece of cardboard on.
Okay.
Well, obviously, there's some place in that cardboard that would balance perfectly, right?
Yeah.
That's called the centroid.
Okay.
And that kind of, it's mathematical in basis, also physics in basis, because when I'm talking about balancing, I'm talking about forces of gravity acting on that piece of cardboard.
Yeah.
So it does have a pure mathematical definition, but it's easier to picture from a physics point of view. It's the balance point. If my piece of cardboard is uniform, if it's 2 inches thick over here and only 1 inch thick there, then it's meaningless. But mathematically speaking, this is called a planar. You might not hear that expression for a few years, but it is a uniformly thick, same density piece of flat material. In this case, it's in the shape of a triangle. And if I want to find the centroid, I would do the median of a triangle. And the median is where you start from the vertex and you go to the middle of the opposite side. So when I did perpendicular bisectors, I started from the middle, but I went up perpendicularly. Here I'm going to connect it to that vertex. Okay?
Okay.
And do the other side. I'm going to connect that to the vertex. And finally, this side, I'm going to connect to the middle. And all three of those cross at the same point also. And that's called a centroid, and that would be the center of mass.
Okay. That makes sense, yeah.
Well, it's a bit odd that you can first of all, that all three of these techniques that all intersect. I mean, I find that interesting. That I wouldn't have ever guessed that if I hadn't known that they all intersect at a point. It's not the same point, but you could call each one of them the center. I mean, I can't inscribe a circle in this or outside it, but if that was a piece of cardboard, that would be where I would put my pencil to balance it horizontally. Unfortunately, the way I drew my triangle here, it looks like each of these is perpendicular, and I didn't mean to do that. Let me redraw it just so you can be clear. They're not perpendicular. If I make something that looks almost like a right triangle, it becomes a little clearer. What I'm going to do is I'm going to bisect that side and connect it to the opposite vertex. So you can see that that is not a perpendicular angle. In other words, that's not perpendicular to that. And it also doesn't happen to bisect this angle. It does neither. And I'm just going to work my way around, bisect that, connect it to that side, bisect this, connect it to that side, and all three of them meet at the centroid.
Okay.
Now, the centroid, yeah, these have some special properties also. And, you know, today is all I'm doing is kind of giving you an advanced review of this material. You'll get this in class, and so you'll have to focus on these properties that I'm describing, but it's always easier the second time to pick it up. So it's worth talking here. And here, let me label this thing. And the label is important. When you have a centroid that is at point P, then the distance from this vertex to that centroid is 2/3 of the distance from A to D. In other words, I can write the following equation. AP equals 2/3 of AD. I can also say that BP, the long part of that one, is 2/3 of the entire BF. And CP is 2/3 of CE. And there certainly are practical problems for that, which we'll leave until later. Let's talk about one other, the last one, and that's the altitude of a triangle. And that'll be perfect. We'll cover it in 10 minutes. The altitude of a triangle is the perpendicular segment from a vertex to the opposite side. Here's my triangle. In other words, if I start with that vertex and drop a perpendicular to the opposite side, like that, do the same thing here, do the same thing here. Now, this isn't bisecting the opposite side, it's merely perpendicular to it. And you notice this is the first time we've done that. There's 4 different things you can do. That creates what is called an ortho center. And there are your 4 centers of concurrency. They're called points of concurrency, and there's 4 types. Now, ortho centers, let's see, the property of ortho centers. The only property they have is that they will intersect at some point. There's no other special things. However, there is something interesting about orthocenters, and that's is that they don't have to be inside the triangle. If I have a triangle like that, and I need to connect that vertex to the opposite side with a perpendicular, I got to go down like this and connect with the extension of that opposite side. Okay? And now I'm going to connect that perpendicularly with that. And now I'm going to connect that perpendicular with this side here. So I need to extend that out. There's the perpendicular connection. Well, unfortunately, the way I drew my picture, let's see if I can grab a little more room here. All three of these lines, let me switch to blue. In other words, this vertical, if I extend it, and this vertical, if I extend it backwards, and this vertical, all have an orthocenter that's outside the triangle. Okay? In other words, the only rule about an orthocenter is that those three lines will intersect at some point. They are guaranteed to intersect if you continue them in both directions. All three of them, they will intersect at the same point. And that is the chapter on points of concurrency. So I hope you cover that next. That's actually two subchapters. That's section 5.2 and section 5.3 that we covered today. Those four incenters. I hope they don't skip it and go on to something else and then come back to it, because your best bet is to take it up immediately. Just understand the differences between all four and which one goes with which. That's what you need to memorize. And there's quite a bit of memorizing to do. In other words, you need to know that the circumcenter is created by perpendicular bisectors. You need to know that the incenter is created by angle bisectors. The centroid is created by medians, and the orthocenter is connected by altitudes. This would be called an altitude, just like if you were trying to find the area of that triangle, you would need the base times the altitude, right? Well, the altitude, this is the base, but the height is always measured vertically. So that would be your altitude that you would drop, and that would also be the height of that triangle for determining its area.
All right.
All right. Yeah. All right. That's probably a good place to stop. Like I said, that's just a first review for you. Hopefully next week you'll get lots more about it.
Okay.
All right, Mark?
Yeah.
I will talk to you next week. Have a good one.
All right. Thank you, David.